Now we're going to review Maxwell's equations with the correction to Ampere's law. All of these equations are now summarized as Maxwell's equations. The first equation was Gauss' law, and Gauss' law is the closed surface integral E dot dA, the electric flux through a closed surface, is equal to the charge enclosed by that surface, Q in, divided by epsilon zero, permittivity of free space. And in words, it says that a charge distribution acts as a source of electric field. So when you have a non-zero charge distribution inside a closed surface, this will create an electric flux and therefore an electric field. The second law is Gauss' law in magnetism. So this is the magnetic field version. The total magnetic flux, closed surface integral B dot dA is equal to 0. This is basically stating that because normally this would be proportional to magnetic charge, there are no magnetic monopoles, so there are no separated magnetic charges, unlike in electricity where we have positive and negative charges that can be separated. A positive charge distribution, for example, here would create an electric field. There is no such thing as a north pole distribution or south pole distribution that will create a magnetic field. So Gauss' law in magnetism says the closed surface integral B dot dA is 0, meaning there are no magnetic monopoles. Faraday's law, the third equation, is basically the closed path integral E dot ds is equal to minus the rate of change of magnetic flux d phi b dt. This is basically the EMF induced by the time-varying magnetic flux. It says a time-varying magnetic flux or magnetic field or the area would create an electric field. So an electric field can be created either by using a time-varying magnetic flux or a charge distribution Q. Ampere-Maxwell law, which is the version for the magnetic field, the closed path integral B dot ds is equal to mu 0 times the current enclosed by that path by any surface that is bounded by this path plus the mu 0 times the displacement current epsilon 0 d phi e dt, which is the term introduced by Maxwell, which says that a time-varying electric flux can be thought of as an equivalent current. So an electric current or a time-varying electric flux or electric field creates a magnetic field. A time-varying magnetic flux creates an electric field. A time-varying electric flux creates a magnetic field, or a current creates a magnetic field. So this set of equations, four equations, Gauss' law in magnetism, Faraday's law, and Ampere-Maxwell law, are called Maxwell's equations. And one can calculate electric field and magnetic field from Maxwell equations. Then the force on a charged particle is given by the Lorentz force. F is equal to Q times the electric field, if you know the electric field, plus Q velocity of the charge cross product with the magnetic field it is subject to. So that's the Lorentz force. So in summary, Maxwell's equations tells us what creates an electric field and what creates a magnetic field. Gauss' law, the closed surface integral EdA, the net electric flux through a closed surface is Q in divided by epsilon 0, which tells us a charge distribution acts as a source of electric field or electric flux. There is no such thing as a monopole distribution, a North Pole or South Pole distribution. Therefore, Gauss law in magnetism tells us the total magnetic flux through a closed surface must be equal to 0. Faraday's law tells us that a time-varying magnetic flux induces an EMF, E dot ds. This basically implies that an electric field can be created by a time-varying magnetic flux. Ampere-Maxwell law tells us that a steady current or a time-varying electric flux can create a magnetic field. The closed path integral B dot ds is mu 0 I plus mu 0 times the displacement current, which is epsilon 0 d phi e dt. And you can calculate electric and magnetic field using Maxwell's equations, and the force on a charged particle is the Lorentz force, QE plus QV cross B, where V is the velocity of the charge, Q.